Welcome back to another video on practical electronics and circuits. In this series, I explain the basics of the theory behind circuits with a focus on using this knowledge for actual projects. In today's video, I'll be giving an introduction to resistors and potentiometers, and we'll also be talking a bit more about LEDs. By the end of the video, you should have a good understanding of what these components are and how to use them in basic circuits. So let's get started and talk about resistors. I'll first go over how to read the color codes to determine resistance values, and then I'll get into the details of how resistors work and give a few examples of how they can be used. Alright, so let's get into it. Now, most resistors will have colored bands on them to indicate their resistance value and their tolerance, like these smaller ones here. Typically, the resistors that have a higher power rating, such as these white ones, or this one encased in metal, will have their numerical values printed directly on them. But the vast majority of resistors are too small to print numbers and letters on them, which is why they have color codes instead. You can search online for resistor color codes and find a chart such as this one. The majority of resistors will either have 4 or 5 bands. The gap between bands will indicate which way to orientate the resistor when reading it. You want to orientate it like this so that there is a single band on the right that's separated from the rest. If you have a 5-band resistor, then the first 3 bands will give you the significant figures, and the 4th band will give you the multiplier. So in this example, we have red, which is 2, then orange, which is 3, then violet, which is 7. This comes out to 237. The 4th band is black, which is an x1 multiplier, so all we do is multiply this by 237, which means this resistor has a resistance of 237 ohms. The last band that's on its own at the end indicates the tolerance, which tells us how accurate its value will be. In this case, it's brown, which indicates a 1% tolerance. This means that its actual value will be within 1% of the given value. So 1% of 237 is roughly 2 ohms, meaning its actual value is guaranteed to be somewhere between 235 and 239. Let's take a look at the 4-band example now. The first 2 values are the significant figures. Green is 5 and blue is 6, which gives us 56. The multiplier in this one is yellow, which indicates a 10K multiplier. So all we do is multiply 56 times 10,000, which gives us 560 kilo ohms for this one. This one has a gold band for its tolerance rating, which indicates 5%. This is worse than the previous example because now the actual resistance is only guaranteed to be within 5% of its given value. Now let's talk about the difference between resistors in series and resistors in parallel. When resistors are in series, you can simply add their resistance values together. So right here I have two 10K resistors. 10K and 10, this should be 10K. So if I measure the resistance across both of them, we get 20K, which means that we could replace both of these in a circuit with just a single 20K resistor if we wanted to. Now, if these resistors were placed in parallel, for example like this, we would not get 20K when measuring across them. Instead, we need to follow this equation here. We take 1 over the resistance value for each resistor and add them all together, then take that answer and divide 1 by that answer. So with two 10K resistors following this equation, we should get 5K. And that's what we see. And if we had more than 2 resistors, we would just, again, take all of them, 1 divided by the resistance value, and add all of them together, then divide all that by 1. Now that we have the basics out of the way, let's now dig into some theory to gain an understanding of what resistors are actually doing. So as their name implies, resistors resist the current that flows through them, but this statement has several implications. In the first video, I explained the water analogy and how resistance can be thought of as a windmill that does work for us. But in order for it to do this work, it resists the water current or essentially slows it down. While a resistor has the same effect as a load does on a circuit, the only difference is that the resistor isn't doing any work for us. Instead of doing work, the resistor is basically eating up energy and releases it as heat. So let's look at a simple circuit with a resistor as the load. Let's say the voltage is set to 9 volts and we're asked to find the current based on various resistance values. Let's first try a 100 ohm resistor. Well, in that case, the current would be 90 milliamps. Now, if we swapped out the 100 ohm resistor for a 1 kilo ohm resistor, now the current would only be 9 milliamps. You can see how higher resistance values lead to less current going through the path for a given voltage. Now let's do an example of how resistors can be used to limit the current. Let's take a look at the simple LED circuit I showed in the last video and explain it in more detail this time. The resistor here is acting as a current limiting resistor in order to protect the LED from too much current. Now, LEDs are actually a type of diode, but I'll be explaining diodes in more detail in a future video. For now, all we need to know are two things about the LED. The first is its forward voltage, which is about 1.9 volts, since this is a red LED. Green and blue LEDs are closer to 3 volts. The other thing we need to know is its maximum current, which is typically 20 milliamps for small LEDs like this one. You can find this info in your particular LED's datasheet or directly on store pages such as Amazon or eBay. In the last video I used a 1 kilo ohm resistor and we found that the total current to be around 7 milliamps by measuring it with a multimeter. But now let's find out how to calculate this without measuring anything. First, we have a 9 volt power rail, which means the total voltage across the resistor and the LED needs to add up to 9 volts. We know the LED has a forward voltage of 1.9 volts. So now we subtract 1.9 from the power supply's voltage in order to get the voltage drop across the resistor, which is about 7.1 volts. Now we can calculate the current since we know our resistor has a value of 1 kilo ohm. This comes out to 7.1 milliamps, which is exactly what we measured it to be in the previous video. But this LED's maximum current is 20 milliamps. We can control the brightness of the LED by controlling how much current passes through it, and we can control how much current passes through it by changing our resistor. So let's say we wanted to run the LED at maximum brightness. All we would need to do is enter 20 milliamps into the previous equation and solve for resistance this time. We get a resistance value of 355 ohms. So now I'll replace our 1 kilo ohm resistor with one that's around 355. But first let's see how bright it was with the 1K resistor. So that's how it is with the 1K. So now I'll swap it out for the 355. I think this is actually 360, but close enough. And now let's see how bright it is. So yeah, you can see it is a bit brighter. It's noticeably brighter. Now, if you were to put a smaller resistor value of, let's say, 100 ohms, then chances are the LED would overheat and burn out from too much current. Also, I'd like to mention that there are special ICs designed to control LEDs without a resistor. They do this by regulating the current, and they're more power efficient than using resistors, since resistors consume power in addition to the LEDs consuming power. But these ICs add complexity and cost, which is why the resistor method is commonly used instead, despite being less power efficient. So with that said, let's now talk about power ratings for resistors. The majority of resistors you'll use in a typical project will be these tiny quarter-watt resistors, since most signals don't use much current. But occasionally you will need resistors that can handle more power. You can find half-watt, 1-watt, 2-watt, and 3-watt resistors that look similar to the quarter-watt ones, but are just larger in size. But their appearance starts to change a lot when you get into the higher power ratings. These white ones here are cement resistors that can handle up to 5 watts. and this bronze one has a metal casing that can handle up to a whopping 50 watts. But now the question becomes, how do you determine if you need a resistor that has a higher power rating or not? Well, let's find out. In our previous example, our LED was using 20 milliamps to attain maximum brightness. And actually, let's go ahead and measure that to verify, since I forgot to do that. So, get this. Let me get this connected really fast. Alright. So yeah, you can see 19 milliamps, which is really close to 20. So anyway, back to power. Well, to figure out how many watts the resistor is consuming, all we need to do is multiply the amount of current that's flowing through it times the voltage drop across it. In this case, it's 7.1 volts times about 20 milliamps equals 0.142 watts, or 142 milliwatts. Since this is a quarter watt resistor, it can handle that just fine. But let's say we wanted to power a bigger LED. Here I have a much more powerful LED, and it's actually an RGB LED, meaning it has 3 separate LEDs. One for red, one for green, and one for blue. Each one of these is rated for up to 700 milliamps instead of just 20 milliamps like our smaller LED. It uses so much power that I had to mount it to this heatsink just to make sure it doesn't overheat. So let's say we used a quarter watt resistor to power one of these big LEDs. Well, 7.1 volts times 700 milliamps equals almost 5 watts, which means our puny little quarter watt resistor would probably burn up and give a little fireworks show if we tried to use it. Of course, we don't have to put 700 milliamps through the LED. We could use the 360 ohm resistor and only put 20 milliamps through the LED, and the resistor would be fine. But then there's not really a point of using such a big LED. So let's say we wanted to get close to its maximum brightness. This is an example where you'd need to use a resistor with a higher power rating, such as these 5 watt cement resistors. But if we wanted to provide 700 milliamps to the LED, we would also need to change the resistance value as well. 7.1 volts divided by 700 milliamps equals roughly 10.1 ohms. Now these particular cement resistors I have are only 5.1 ohms, but if I place 2 of them in series like I did here, that would give 10.2 ohms. So that should work out just fine. Now before turning it on, I'm going to place this plastic cover over it to help diffuse the light because it gets blindingly bright. So I'm going to turn this off, connect it here. Okay. So there you go. Now keep in mind that this is running off a 9 volt power supply, which doesn't do us any favors when it comes to power efficiency. A 5 watt power supply would make a lot more sense here, since the voltage drop across the resistor would be 3.1 volts instead of 7.1 volts like it is now. This means that the resistor would only eat up about 2.2 watts instead of nearly 5 watts like it is now. But doing this also means you would need to change the resistor value in order to maintain 700 milliamps. So instead of using a 10 ohm resistor, we would need a resistor value of around 4.4 ohms to attain maximum brightness with a 5 volt power supply. And before we move on, let's just verify how much current this LED is actually using. So I'll turn this off and disconnect this and get it hooked up to this one. And yeah, we can leave it on the milliamps since I don't expect, well actually 400 milliamps is the limit on this one, so I'm going to switch to the amps to measure this. Don't want to blow out a fuse. Alright, so let's turn it on and see. So yeah, it's using about 500 milliamps. That definitely would have blown the fuse. But actually, we could get this LED a bit brighter if we used slightly smaller resistor value. Not power rating, but, ohms. Also, I realized after filming this that the forward voltage for this LED is higher than 1.9 volts. It's more like 2.1 volts at least, which explains why we're getting a lower than expected current draw given this resistor value. Also, the resistors themselves don't have perfect tolerance. They're going to be off by a bit, so that's why the reading is less than 700 milliamps. So hopefully now you have a better idea of how to use resistors to limit the current. But now let's focus on how resistors impact the voltage and how this can be useful for us. What if we wanted a set current that didn't change? How would changing the resistance value affect the circuit? Well, let's say we start with a 100 ohms resistor and then change it to a 1 kilo ohm resistor. In order for Ohm's law to remain equal, the voltage would also increase proportionally to the resistance value. So from this point of view, the resistor isn't limiting the current, but is creating a voltage drop in the circuit. It brings us back to the point about Ohm's law that I really wanted to reinforce in the first video. There is an intrinsic relationship between the voltage, current, and resistance, and changing one of them has an effect on the others. So while a resistor does resist the current going through it, it also has an effect on the voltage and creates a voltage drop across itself. But how can we use this property to our advantage? Well, let's now talk about voltage dividers. A voltage divider is simply two resistors in series, and the junction where they meet creates a new voltage that's less than the supply voltage. This new voltage can be set to whatever we want by choosing the correct resistance values for these two resistors. We can calculate this voltage by using this equation. So right here I have two resistors on a 9 volt power supply, and both of these resistors are 10 kilo ohms each. If we plug these values into the equation, we get 4.5 volts, which is exactly half of the supply voltage. That's because the two resistors are the same value. Now I'll go ahead and measure the voltage to verify this. So I put this lead on ground on that leg, and then this lead is at the junction, and we see roughly 4.5 volts. Now keep in mind that it's the proportion of these two resistor values in relation to each other that sets the voltage. The resistor values themselves don't matter. In other words, I could replace these two resistors with two 20 ohm resistors, or I could replace them with two 5 mega ohm resistors, and we'd still get the same voltage. But now let's swap R1 with a different value. Let's use 4.7 kilo ohms instead, which is what this resistor is. So plugging this into the equation, we should see a voltage of around 6.1 volts. And yep, that's what we see. Now let's swap these two resistors around so that R2 is the smaller value now. So just give me a second here. Okay, now let's measure. Yep, so that's 2.8 volts, and that's pretty close to 2.9 volts is what you'd get by plugging them into the equation. Now, voltage dividers are pretty common in a wide variety of circuits. Let's quickly take a look at two applications for them. The first can be found in guitar effects pedals or pretty much any audio equipment that uses a DC power supply. The reason is because audio is an AC signal, so we need a way to convert a DC power source into an AC signal. We can do this by creating a virtual ground using a voltage divider with two resistors that are the same value, just like in my previous example. This divided the voltage in half, creating a 4.5 volt signal. If we were to treat this 4.5 volts as a reference, then that would mean anything between 4.5 volts and 9 volts would be considered a positive voltage, and anything between 0 and 4.5 volts would be treated as a negative voltage. Being able to create positive and negative voltages in respect to a reference, or in other words, a virtual ground, now means that we can create audio signals from a DC power source. Another application where voltage dividers are found are in potentiometers, or pots for short. Pots are knobs that we turn in order to control the voltage of a signal. It turns out pots are just a voltage divider, but the middle leg is a wiper that sweeps across its resistive element as you turn the knob. So it's basically an adjustable voltage divider. Let's use this pot as an example. It's a linear 10K pot. That means that its total resistance across the whole pot will always be 10K. So I have this probe hooked up to the wiper in the middle. So let's measure the resistance across this side first. So the knob is turned all the way counterclockwise and we measure 9 kilo ohms, which is close to 10. And now as I move it, you can see it decreases. Now I'm about almost halfway. And now if I keep going all the way, we're now at basically 0 ohms. But now if I were to switch this probe to the other side, so now we're measuring the other resistor, we now see that that's almost 10K. And as I sweep the knob across the other way, we'll see the same effect happening where the resistance on this side is diminishing and it's all being shifted over to the other side of the voltage divider. So now let's plug this into a power supply and measure the voltage. So I'll plug this leg into power, this one into ground, and set the multimeter to voltage. I'll put this leg on ground, and this one is connected to the wiper, which we'll be measuring the voltage for. So I'll turn it on. Since the knob is all the way down, we see 0 volts. Now I'll slowly turn the knob up, and I'll stop at about halfway, which should be 4.5 volts. So yeah, that's roughly halfway. You can see the line across the knob is level. And if I keep on turning it, we'll slowly get to 9 volts. And yeah, it's turned all the way up now, and we have exactly 9 volts. Now, just like resistors, pots also come in different sizes and power ratings. So keep this in mind when working on projects that use a lot of power. Pots also come in different tapers, including linear, logarithmic, and reverse log. All the taper does is modify how quickly the wiper changes the ratio between two resistors. Let's start with a linear pot. If you were to turn the knob all the way down and then slowly turn it up at a consistent rate, a linear pot would create a consistent change in resistance and therefore voltage as well. If you were to graph this change in resistance, it would look like a straight line, hence the name linear pot. A logarithmic pot, on the other hand, produces a non-linear shift. As you begin to turn the pot, the resistance will slowly change until you get about halfway, at which point the change in resistance will rapidly increase as you turn it up all the way. A reverse log does the opposite. It starts off with a rapid change and then slows down as you get to the end. Now, another name for logarithmic pots are audio pots. This is because audio doesn't follow a linear increase in loudness as you increase the power. For example, if you provide double the power to a speaker, you'd expect it to be twice as loud, but that's not the case. It would only become marginally louder. That's because audio follows a logarithmic scale in this regard, which is why logarithmic pots are sometimes called audio pots. They make it so as you turn the knob to increase the volume, you'll get a more consistent increase in loudness as you turn it up. But I'll talk more about this in future videos when I do more audio-related projects. And just like resistors, Pots also come in various values as well. You can typically find them in the range between 1 kiloohm up to 1 megaohm or more. And finally, rheostats are another component that are very similar to pots, but instead of having 3 legs, they only have 2 legs. Instead of being a voltage divider like pots are, rheostats simply change the resistance between its 2 legs. Rheostats aren't as common because they're typically only useful in high power applications. Also, it turns out that pots can actually be used as a rheostat if you only use 2 legs. But the opposite isn't true. A rheostat cannot be used as a potentiometer, which is one reason why pots are more common and useful to have. Well, that wraps up everything I wanted to talk about for today. Hopefully you now have a basic understanding of what resistors are and how to use them in basic circuits. Again, this was just an introduction and there's still quite a bit to talk about in regards to resistance. But I think I covered all the basics and I'll be expanding more on this in future videos as we get started on more projects. If you found this video helpful, then be sure to give it a thumbs up and consider subscribing to the channel and hitting the bell so you can get notified when new videos come out. As always, thanks for watching and I'll see you in the next one.